Right, homework this term, we're going to be revising core practicals, and the first core practical, you would have done it way back in year 9, separating the components in ink. So we will be using chromatography, but the actual core practical, you have to remove the excess solvent. Kind of, if you think of the ink cartridges we use in our board pens, there's obviously dyes in there, but there's also some solvent, and your first step is to remove that solvent, and you're going to do so using distillation. Now you're not typically asked to draw the apparatus for distillation, but you are asked to correct it if it's drawn incorrectly, so I think it's useful to have a look through it. So with distillation, you're always going to start with a round bottomed flask. That is literally the name of it, not a conical flask, always a round bottomed flask. You will be heating your mixture of ink in your round bottom flask. The solvent, which is typically water, will start to evaporate. You obviously don't want it to escape, so attached to that round bottom flask you are going to have a delivery tube, which is going to look something like this. Okay, this has to be sealed. You don't want all the vapor to escape out from the top, and we also use a thermometer to keep track of the temperature of that water vapor. Important point here, the thermometer, so the bulb of the thermometer, which is the bit that actually measures the temperature, should not be in the mixture. The bulb of the thermometer should be level with the delivery tube. You're using the thermometer to get the temperature of the vapor, not to get the temperature of the liquid itself. So that's where your thermometer should be. At the end of your tube, you have to have some sort of a receiving vessel. That can be your conical flask. This is where you are going to collect your liquid. Obviously, to speed this process up massively, you want to keep this tube nice and cold, and so you typically have a condenser around it. So condenser is going to look like this. And it basically gives you this supply of cold water, so that you get water coming in from the bottom. You connect it to the sink, you've got water coming in from the bottom, going out at the top, and you've got this constant supply of fresh water going around your delivery tube and keeping the delivery tube nice and cold. That's going to make it easier to condense your vapor. Other question they ask you about this is the condenser. They can have the labels the wrong way around, so that water is coming in at the top and out at the bottom. The reason that's incorrect is that the whole condenser won't fill. If you go in at the top, the water will just come down here and out here, and this whole portion here at the top won't be full and won't be cold. By putting it in at the bottom, it fills slightly more slowly from the bottom, but then you get water going around all of the delivery tube and keeping it super cold. So really important it goes in at the bottom. Distillation should be an open system. What I mean by that is it's not totally sealed. Yes, it's sealed here, but then it's open here, so you are able to heat it without worrying about high pressure. So often they give you pictures of more simple apparatus than what I've drawn above. So this is your kind of best case scenario, but they can give you something that looks more simple and ask you to correct it or improve it. So if we look at the first example here, if you're heating the substance that's in this conical flask, they asked what was wrong with this apparatus. All right, it's open here at the top. Your water vapor is just going to be able to escape out the side. It's not all going to be in the delivery tube, so you would have to seal it in order for the vapor to enter this test tube. The other thing you could do to improve it would be to add ice around this tube to keep it nice and cool and make the process more efficient. This was another one that they asked you to improve. This one here is already sealed, so that's not an issue. When I was marking this, a lot of people said, oh, you seal it on this side as well. You can't seal it on both sides. When you're heating something, you can have a buildup of pressure. It is dangerous, so one side has to be open. This side has to be sealed because the vapor needs to go into the tube, but this side is going to be open because it's coming out as liquid water, and the liquid water is just going to pass down here. It's not going to be able to, the liquid water can't jump up here and escape, so it's not a problem and it makes it safer. But for this particular one, they wanted you to say that you would, add ice around the delivery tube to cool it and make condensing more efficient. They didn't allow you to say add a condenser. They wanted you to explain how you could change this particular or improve this particular piece of apparatus, assuming that you didn't have access to something more sophisticated. So just by cooling it down using an ice pack or something, that's all they allowed you to say. All right, have a go at doing questions 1, 2, and 3. From quiz 2. Alright, so answers. First one, just distillation, if you're just trying to remove the solvent. 3 things. This was an exam question a while ago. So the thermometer bulb is too low. Okay, it needs to be level with the condenser. You're getting the temperature of the water vapor, and therefore it needs to be at the condenser. Water in and out, it should be going in at the bottom, out at the top. The reason, and they did ask for this one year, is so that the entire condenser fills. And then the beaker, it needs to be under condenser, or otherwise your solvent or whatever it is you're collecting is going to miss and just end up on the floor. Alright, so just move that beaker over. How could you prove the solvent was pure water? Very simple test. Heat it. Use a thermometer, check the boiling point. If it's 100 degrees, it's going to be water. That was a 3-mark exam question one year. 1 mark for heat, 1 mark for use thermometer to check boiling point, and then stating the boiling point of water is 100 degrees. Alright, once you've removed the solvent from ink, you then need to separate out the different coloured components, and you're going to do that using chromatography. Chromatography, you've always got a stationary phase. That's the bit that doesn't move. That's your chromatography paper. And then you've got a mobile phase, the bit that does move. That is your solvent. Often water, but you can use an organic solvent like ethanol or propanone. In terms of how chromatography actually works, all right, if you have a look at it over here, I've got my piece of paper. I've drawn a start line, I've drawn this in pencil, and I've got my mixture here. It's made up of X, Y, and Z, and I've put a dot of my mixture on my start line. What I'm then going to do is I'm going to place my stationary phase, my paper, into the mobile phase, my solvent. So I'm just going to draw a beaker here, and I'm going to place it in my solvent. You'll notice that the solvent is starting below the start line. If you plunge it straight in, everything just runs and smudges. So what you want to happen is you want the solvent to move up the chromatography paper, and as the solvent rises, it carries the different components of the mixtures different distances based on their solubility. So if X is super soluble in water, it will stay with the water, and anywhere the water goes, so does X. And if water rises right to the top of the paper, so will X. If Y is insoluble, doesn't dissolve at all, then Y won't go anywhere with water and it will stay put. So I can separate out X, Y, and Z based on their different solubilities in my mobile phase. If we look at what this might look like at the end, okay, so X, you can see, has travelled the furthest. That means X is the most soluble in water. Y has kind of made it to the midpoint. Z hasn't moved from the start line at all. So that tells me that Z is insoluble in water, and that's why it hasn't moved. If I wanted to correct this and analyse Z, I would need to use a different solvent. So it's not dissolving in water. Maybe it will dissolve in ethanol. So I would have to try it again with another solvent. You'll see here I have marked my solvent front. That's the distance that I allowed the water travel. The reason you need to do this is when you're calculating the RF value, you're going to need to take that measurement. So the RF value is the distance moved by your spot divided by the distance moved by your solvent. So I would take a ruler and I want to calculate it for Y. I use my ruler and I see, oh, Y moved 3 centimeters from the start line. Then I looked at how far the solvent moved in total, and I see it moved 6 centimeters in total. So my RF value is going to be 3 over 6. It's going to be 0.5 centimeters, but your units are going to cancel, so RF doesn't have any units. Because the solvent will always move further than the spot can't outrun the solvent, you'll always have your biggest number on the bottom, which means your answer will always be less than 1. So if you've got an answer greater than 1, you have done something wrong. So we mark the solvent front to calculate the RF value. That's also why we draw a start line. Okay, we need to see where they started so you can calculate the distance that they travelled. So that's why we're going to draw a start line. Draw that start line in pencil. If you draw it in pen is likely soluble in your solvent, and the start line will travel as well, which we don't want to happen. In terms of why we actually calculate these RF values, all right, if you're trying to identify some sort of unknown, you don't know what it is, you can look at a database. If you've used the same solvent that they have on the database, you can compare the RF value you got with the RF values they have and use that to potentially identify some sort of unknown sample. Right, other than that, have a go at questions 4 to 10. Alright, 4 is just chromatography. 5, mobile phase is the solvent. Don't say water, it doesn't have to be water, it's just whatever solvent they've used. Stationary phase is always the paper. There are your only correct answers. Number 6, just look how I phrase this. Alright, the components of a mixture travel different distances up the stationary phase, and this is based on their solubilities in the mobile phase. So I've included loads of keywords there: stationary phase, mobile phase, and I've told you that the separation is based on their solubility in that mobile phase. Alright, so that's how you would phrase that answer there to get all of your marks. Why are we drawing the start line in pencil? Don't just say because pen would smudge, okay? You have to tell me the pencil is insoluble in the mobile phase, so it will not move. Or you could reverse that and say pen is soluble in the mobile phase and will move, but you should be using those words soluble / insoluble and that word mobile phase. Why do we need a start line? You're going to use to calculate the RF value. You could also say so that all of your, if you're separating multiple mixtures, so that you're starting them all in the same place. But yeah, calculate RF value will always get you the marks. Results of the chromatography. So you have got 0.67. The greatest RF value is going to be the one that is most soluble. It travelled the furthest, so that's 3 or green. And then 1 and 4, 1 is 0.1, blue is 0.12, so they're very similar RF values. They haven't been fully separated, which means they're going to be appearing on top of each other, and if you've got yellow and blue on top of each other mixed together, it's going to look green. So that's what it's most likely going to look like. There's 1 or 2 exam questions to do as well. One asks you about the accurate, how you can make it more accurate. If you use a longer piece of chromatography paper, you get a better separation. So that'll be the answer on one of your other questions. I think we've covered everything else. Yeah, chromatography.